Okay, children, good evening. Can you hear me?
Good evening.
Good evening, right? Okay, so I'm going to start this chapter 16. The session is recorded. So if someone misses, they can go through this. So this is a small chapter. These are the theory chapters, right? Mm, that they would be making questions for the theory paper. So this one is talking about machines and computational models. Right, you know what models are, right? Models, they represent a real world scenario. They are used to test the real world scenario in the computer. There can be different types of models. So we'll talk about that in this chapter. And you know that any computer or any device would have, I'll share the screenshots in the group so that you can highlight your book. You can highlight your book even right now when I'm going through this section. Let me see whether I can highlight. If I highlight, yeah, it lags a little bit. So I'm not going to highlight here, but anyway, I'll share the screenshot in the WhatsApp group so that you can do it later, right? Or even now when I'm talking about certain areas. Our
Good
video is on.
good evening, sir.
Good evening.
Should I say good night or good evening?
We'll say good night
Sir.
after we finish, right? Yeah, let's say good evening.
Good evening, sir.
Never mind, never mind. Whatever it is, never mind. Let's do this fast. So if you take any device like this, whether it's a computer or a smart device, you can interrupt me anytime and ask questions, no problem, right? And
Yeah, okay, sir.
with the input, process, and output in any of these, there'll be input, process, output. So that's the basic model that we have in any device, across any device. So it can be represented like this using a flow chart. Input, process, output. The order is there. What is missing here is the storage. Later on, when you learn about von Neumann architecture, you will see how the storage was added to this. So we can store the data and information and we can use them later on. So storage is missing here, but the basic process is input, process, and output, basic stages. You might be surprised to know that every device shown on the analysis contains an embedded computer. Now, what is an embedded computer? There's a chip, there's a microchip built into the car, the washing machine, organ, all these devices. So they are programmed with some instructions. When you power them up, they will execute these instructions and do some work. Feel free to ask questions, raise hand or just disturb me anytime, no problem. A computer is a machine that takes some kind of input from its surrounding, processes the input according to the given rules, and provides some kind of output. Right. But you know, even though computer and the embedded device has this input process output model, embedded devices are different from computers. Because computer is a machine that can be used for a variety of tasks. Whereas embedded device like washing machine, microwave oven, refrigerator, they can do only a dedicated set of limited tasks. Right? They can't be programmed to do other tasks. Okay, but they both have the same model: input, process, output, and storage also. You're probably familiar with the desktop computer. The keyboard provides input and the screen provides output, which depends on what you type. In a similar way, the embedded computer in a washing machine has controls, which will be the input. Then the motor, heater, will be the outputs. Got it? And spinning, you know, rinsing will be process. Understood?
Yes, sir.
Yeah. If you didn't understand, if you want me to explain again, let me know. Right. The clever bit in computer science is the activity that goes on between the inputs and outputs, the processing. The processing means performing a series of actions on inputs. Okay, let me take a screenshot and highlight, then you also can highlight. Okay, I think you better highlight when I highlight here. Right, processing means performing series of actions on the inputs according to the given set of rules. You might have might have met this idea in maths already if you have studied function machine. Have you learned function machine in maths?
I am not sure, sir.
Not sure. Right.
Not sure.
Function machine is a metaphor or diagram that represents a machine that takes as input, applies a rule, and gives an answer. So basically, a computing
So
device.
it's a condition. It's a condition like. Is
Exactly.
it like a condition?
Exactly. Take some input and do something and outputs information. A function machine. In Unit 1, page 4, an algorithm was defined as a precise method for solving a problem consisting of a sequence of step-by-step instructions. In order for processing to produce meaningful results, it has to follow an algorithm. What is an algorithm? It's a step-by-step process to a solution. And how did we do algorithms? We used pseudocodes, we used flowcharts, and we used structured English or written description. So you might also think of an algorithm as a sequence of steps that is used to process the input and produce the output. So something like this, you input 3, multiply by 2, you get 6, add 2, you get 8, and you output 8. So there is a sequence, right? This has to be done before you multiply by 2, right? You have to multiply by 2 before you add 2. If you try to follow a more complicated function machine than this one, you will probably need to keep track of your working. In a similar way, anything beyond the simplest algorithm needs temporary storage or memory. We should change our diagram of a computer to include this. What does that mean? Right? If you want to have more functions, you will have to store values temporarily. Then just inputting, processing, and outputting is not enough. We need a storage, maybe a temporary storage, maybe a permanent storage.
So like auto start applications, those have temporary storages, right?
Yeah, I mean, like when we were,
Like virus cards and whatnot.
yeah,
On PC,
yes,
it'll be okay, sir.
okay, right. So when you were writing programs, we used to have variables. So those variables were holding values temporarily in RAM. Then we didn't do file handling. When you do file handling, what we do is we bring data from the permanent storage into the RAM and then work on them. So that's why I told you, like, it can be RAM, temporary memory, or it can be secondary storage. Just give me a minute. All right. So I hope you understood up to that point. Let's move on. Okay, here comes. Now the diagram is updated with the storage. Okay, so the storage can be RAM or it can be permanent storage also, or the hard drive. But you know that even when you take something from the hard drive, in order for that to be processed, it has to come to the RAM. So it is brought from the hard drive to the RAM, and from the RAM to the processor, registers in the processor. And then there's cache also, cache memory also. We'll talk about that later on, right? I don't think we have to do that in this term. Okay. Range of computation models. Right now, you know about the basic process, basic set of stages: input, process, output, and then storage. So based on this, there are different types of scenarios that we come across, different types of applications, right? These are called computational models. Any question? Just disturb me anytime. Huh? Okay. Right. Computational models describe, highlight this, how algorithms are executed by machines. So all these computational models are going to have those stages: input, process, output, and storage. But these are different from the way they do it. There are different models of how this process can be carried out. Sequential. Right. Sanula, can you tell me what is sequential? What's the meaning of sequential? The general meaning of sequential. Sanula? Okay, what about Tharul? Okay, what about Meeda? What do you mean by sequential? Okay, no one is responding. What about Shuhagi? Amar, wait. Vishal? I see, no one is responding. Alia, what do you understand by sequential? Yeah, Amar.
So it's going by in like one after the other, like
One
step
after the
by
other.
step.
Yes, one after the other in order, right? So feel
Yes,
free
sir.
to speak, will you? Don't keep quiet. Just say something. Doesn't matter, even if you get it wrong. Right. So sequential model is where the instructions are carried out one after the other, step by step, in order. Highlight, step by step, in order. So one step has to be finished before the other step is started. Simple. Okay. For example, let's say, what can you say? Can you give me a real world example of a sequential
Uh,
model?
when making a recipe, normally they'll go step by
Okay,
step.
okay. But how about an IT one? Yeah. IT one, IT related one.
So could you say math equations? But is it IT related? Because
Yeah, okay, okay.
like,
No problem. Like, okay, let's say a calculator or something, right? You
yes,
enter the first number, you enter the second number, then you enter the. Naila, are you going to say something?
Okay.
Yeah, any idea? Anything to add? No, right. Okay, then you enter the operator and then only you get the result, something like that, right? Or if you take a real world example, yes, cooking, yes, you have to do it in order. Maybe even starting a vehicle and moving has to be done in order. You have to start the engine first before you move, right? Unless you push it. So sequential. Then comes parallel. Parallel. Well, you know what parallel is. Computer processes are distributed between two or more processes. Now, what are these processes? Two or more processes. Do you know that these are called, you know what these are called? These processes? Modern day processor is actually a collection of small processes.
Transist.
It's not a single processor. Those days it was just a processor, but now it's a collection of small processors. What do you call these small processors?
Transistors?
No,
The
Uh,
microchips?
oh, yeah.
no. I mean, they are made up of transistors, but then you have to go to the microscopic level. But if you take a processor or the CPU, let's say the CPU, this is consisting of small processors built into one unit. Small process built into one unit. What are these called? These small processes.
Sub processors.
Uh, these are called cores. Cores.
Okay,
Okay. So that's why we call dual core, multi core, hexa core, octa core, right? So we are having cores, right? Because of cores, right? When one core is handling one instruction, another core will handle another instruction. So we have true parallel processing with a multi-core system, right? Otherwise, when we had a single core processor, this core had to switch between the tasks, right? Quickly, right? It does a little bit of this and a little bit of this switching, but that was not true parallel processing. So with this, we have dedicated processors, which are called cores, looking into different instructions, and it is happening at the same time. So we have a parallel system. So a computer with two or more processors installed. So remember, these processors are cores. Each separate part of the algorithm that each processor processes can be combined together, right? So this can be like, let's say, if you have a small program of adding two numbers and outputting the total, one core can handle inputting of one number, while the other core is handling the inputting of this second number, right? It can be like one core doing one whole program and the other core doing another whole program, or even the same program is divided among these cores, right? It requires an operating system capable of supporting two or more processes, right? So it is the operating system which supports this dividing of, you know, processors, not the hardware process, the processors, the tasks among the cores. It also requires software programs capable of distributing the process between them equally. Okay, so what happens is when you have a program like this, okay, and when it has instructions like this, right, there will be the OS which is coming here and looking at these parts of the codes and distributing them among different cores, right? So that, instructions that can be carried out parallelly can be done parallelly. But certain instructions you can't, you have to do it sequentially, right? I mean, for example, inputting those two numbers, right? You can't enter usually you don't enter the two numbers at the same time. Yeah, Amar.
Yeah, I was putting a thumbs up.
Right, okay. Right. So certain instructions that can be carried out parallelly are distributed among multiple cores. Certain instructions which cannot be done parallelly will have to be done sequentially. Okay. So in a parallel model, you have multi-core system. Understand? Okay. I'm going to share the screenshot so that you can Take a look at it later on. Okay.
So,
Finally, yeah.
what type of functions that the core has to do sequentially in the single core instead of separating amongst each core in the processor?
Yeah, that's what I told you. Like, if you have to enter two numbers, okay, and if you are entering these two numbers in two occasions, so you enter number one first, and after that only you enter the second number.
Yes, sir, I never that, but then you told that there are some processes that has to be done only in one core instead of
No,
dividing.
not one core actually. What I meant was certain instructions have to be carried out sequentially. Certain instructions can be carried out parallelly. So if it
Okay,
is carried out parallelly, it can be distributed among several processes. I mean, it's
okay,
something like this. Teacher wants to get something done from you, right? So there will be a team of you. What teacher does is she will divide that work among the members, and then the outcome will be joined together.
mhm.
That's like
Yes,
parallel processing, right? But when a task is given like that, certain things you can't do it in parallel, right?
yes, sir.
I
Yeah,
mean, let's
okay,
say you had to do a poster, uh, and teacher uh, assign someone to find information. So until she finds information, others can't create the poster, something like that. But certain things can be done in parallel. Okay, right. So the final
yes, sir.
model is multi-agent. Multi-agent. Now this is something like this. This is a more complex model, right? Okay, let me take a screenshot. Okay. In the parallel model, one task is processed by several processes, while in the multi-agent, highlight this, in multi-agent model, separate tasks or algorithms are processed by different systems, right? Different systems. These systems are called agents. Agents. So it's not this agent is not a core. It's not a processor. It is a system, complete system. You can think of it as like a mainframe computer or a mini computer, a powerful computer, right? Each agent acts independently under its own control. So it has its own system, own hardware and software resources, right? And the other thing is agent is autonomous, which means it is using AI and it works on its own. It's pre-programmed, it works on its own, and it can take decisions on its own. But they cooperate with each other through negotiation and coordination. Right? These agents, these machines, they can talk to one another and they can coordinate the work. So this is like a distributed system, right? And these agents can be in different places, like maybe in different countries even, right? So imagine something like big data processing. It has to be distributed among um, several systems around the world or maybe around a place. It can't be handled by one system. So then there should be a complex system. So these agents, they negotiate, they talk to each other, they coordinate, they distribute the work, right? And for that, we need artificial intelligence. Okay. Where independent agents, like just like the human society, right? Just like the human society, you guys will be agents. And what do? You think, you decide, you take decisions, and then you talk to other people. You make them take decisions, right? Uh, so there is a kind of a interaction. Okay. Searching the internet for the answer for a specific query can be a long and boring process that could be done for us by an agent. A computer program instead would give the query details of what we need to find out. This would require the agent taking information from various sources. I mean, yeah, for example, a search engine, right? So Google search engine, for example, it uses AI, and imagine the number of results it produces within fraction of a second, bringing all this information into one place. If we were organizing a holiday, we could communicate our preferences, and different agents could cooperate to search and compare different deals, negotiate for their best prices, plan, transport, book airlines, right? They could even order suntan lotion or book restaurants for us without our direct involvement. So you can see here we are talking about uh, what we experience today, right? When we search for something, we are being displayed similar content, similar advertisements, right? When we post something in social network, we get related emails. When we send an email, we get related posts on social network. So these are handled by agents, AI agents, models, right? They always monitor our activity, right? They take decisions and they compare, they handle huge amounts of data, taking decisions. So they can't be run on simple machines. They had to be run on, distributed systems, mainframe computers. Okay, so the key characteristic of multi-agent is that these are systems, complete systems. They are powered by AI. They are autonomous, and these agents can be distributed around the world, and they can take decisions, they can talk to each other, and they can handle large amounts of data, and they can monitor the activity. Okay, understand? Any questions? Anyone? Any question?
I don't think so, sir. It's
Yeah, others, are
it's
they
nice.
sleeping? Others, let's talk to Mokiza. Mokiza, did you understand?
Yes, sir.
Right, okay. Wait, right? Okay. What about Nabil? Nabil bro. Nabil bro, are you there? Okay, he's chatting, right? Okay, fine. Right, just a quick recap. We were talking about computational models, and there were three models: sequential, parallel, and multi-agent. And sequential was executing instructions one after the other in an order, and then parallel was where uh, the tasks were distributed among cores, several processes, but it was still within a single machine. But when it comes to multi-agent, we are talking about complex systems where we talk about agents, complete systems which use uh, artificial intelligence, and they are autonomous, and they negotiate, talk to each other, take decisions, and monitor. Right. That's it. Just a minute. This is lagging too much. So now you can mark in that scheme of work. We were supposed to do 16, chapter 16, 160 to 164, which we have done. So can you mark that? Next is hardware, then we have logic, we have software. Okay, so there are some questions. This I will give for homework, right? Okay, before moving to the next section, let me take the binary chapter. Let me go to the binary chapter and do the last part, right? Because I did that with one class today. But the other class we can do it. So let's go back to the binary chapter. Can you go to the binary chapter? So 2's complement, yeah, 2's complement is there. We did 2's complement, sign and magnitude we did. These shifts won't be tested. Binary shifts, logical shifts won't be there. Arithmetic shifts won't be there. And let's jump into the last part, this one, which I did with one class today.
Yeah, so you did it with us.
Yes.
We-
So I'll do it once again for all of you, right?
Okay, so-
Right. Because this is a small part which we cannot miss. Okay, this one is about hexadecimal. Hexadecimal. Okay, so those who did the lesson today, can you tell me in hexadecimal how many numbers are there?
0 to 15.
Is
16
16?
numbers.
0 to 15, 16 numbers, right? So those who didn't do it today, the other group, listen very carefully, right? So we are talking about a number system called hexadecimal. Hexadecimal, right? Hexa means 6, decimal means 10. So this is base 16. In base 16, we have numbers 0 to 9, the normal denary numbers. And after that, we have 10, 11, 12, 13, 14, 15, not 16. So 0 to 15. Now the problem is when it comes to 10, 11, it can be misinterpreted as binary or hexadecimal or even denary, because when I write 1 0, this can be 10, this can be 1 0 in binary, this can be 10 in hexadecimal also. So to avoid that confusion, what they have done is they have put alphabetical letters to these numbers. So 10 is A, this is B, C, D, E, and F. So the numbers in hexadecimal range from 0 to F, right? 0 to F. Right. Now the next thing is, now this section talks about converting binary to hexadecimal and hexadecimal to binary. Binary to hexadecimal and hexadecimal to binary. Okay. Now before doing that, we need to know how many binary digits or bits are required to represent a hexadecimal number. You know that when you have one bit, you can represent 2 to the power 1 numbers, which is 2, which can be either 1 or 0. Okay. If you have 2 bits, these are bits, okay? You can have 2 to the power 2, which is 4. So you can have 4 combinations, 4 numbers. That is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, now tell me, if I want to show 16 values, how many bits I need? Those who did today, don't say it. The other group, if I want to show 16 numbers, how many bits I need? Anyone from the other group?
4.
4, good. 4. 4 bits. How? 2 to the power 4 is 16. So we need 4 bits to represent 16 numbers. That means if you want to represent a hexadecimal number in binary, you need 4 bits. 4 bits. Okay. Right. So having understood that, let's see how we can convert binary numbers into hexadecimal. Right. Okay, let's take a binary number like this: 1 1 0 1 1 0 1 1. Okay, all you got to do is, it's really easy, right? All you got to do is just start from the right corner and group these binary numbers, bits, into groups of 4. 1 2 3 4. 1 2 3 4. Why 4? Because you need 4 bits to represent a hexadecimal number. So just group the bits into groups of 4. Now, a group of 4 bits is called a nibble. A nibble. Right. Okay. So what we do is we, yeah. Can you hear me?
Yes.
Right. So you start from the right corner and then you group it into nibbles. Group of 8 bits is called 1 byte and group of 4 bits is called a nibble. And then what you do is you convert each nibble into a denary number, right? How do you do that? We did in the first lesson. We write the positional values 1 2 4 8 1 2 4 8, and then you convert that into the corresponding denary number. This is 1 8 1 2 1 1. This is 11. This one, if I do a mistake, let me know. This is 12 and 13. Right now, you can't show 13 and 11 like this, right? Because in denary, this is 1311. So we can't represent like that. So what we do is 13 is represented as D and 11 is represented as B. So the answer is DB. Got it? Easy, right? Any questions? Anyone found it confusing? Difficult? Right? That is binary to denary. Binary to denary. Okay, let's look at the opposite, and after that we'll do a couple of questions, right? Okay. This is oh sorry, it's not binary to denary. It's binary to what?
The
Binary to
hexadecimal.
hexadecimal, yes. Ah, later. Binary to hex. Okay, this is the opposite. Hexadecimal to binary. Right. Exact opposite. Let's say we have something like this. A5. All you got to do is just divide the two and represent each number, each hexadecimal number in 4 bits or a nibble, 4 bits. Right now, to make sure that you don't do mistakes, the easiest way is you write the positional values for 4 bits. That's 1, 2, 4, 8. 1, 2, 4, 8. Okay. And let's put 5 into this. If it is 5, there's no 8s. There's 1, 4. And there's no 2s. And there's 1, 1. Okay. 1, 0, 1. That's 5. 0, 1, 0, 1. Because we had to use 4 bits. This one, A. What is A? What is A, Roshda? What is A? Roshda, what is A? Tiloshana, what is A?
13.
10, yes. Okay, it's 10. So if it is 10, we have 1, 8, no 0, no 4s, 1, 2, no 1s. 8 plus 2 is 10. Now what you do is you join these two and write as one answer. 1, 0, 1, 0, 0, 1, 0, 1. Is that correct? 1, 0, 1, 0, 0, 1, 0, 1. Okay, easy, right? That's how you convert hexadecimal into binary. Okay, any questions, any doubts? Okay, let me share this. Right, let's take a couple of questions, right?
So for hexadecimal, you just go back up the chain instead of, because I thought you're supposed, after you turn it into a denary number, we add it together and then convert that back into binary.
If you want to,
So when turning it back to binary, the
okay,
method I did before. at school was get the denary values and then add it together. But now it's now it's wrong.
All right. Okay. All right. Right. So let's take one example, and the rest I'm going to give for homework. Let's take this one. A6 is fine. Okay, let's take 9C. No, we'll take this one, B, 1B, 1B. Can you also do it? Take your exercise book and do it together. Let's do it together. Let's take B, yeah? B. Uh, 100. Triple 100. Right. This has to be converted to hexadecimal. What you do is you start from the right corner. Do it in your exercise book. 1, 2. Wait a minute. Right. You start from right corner and you group them into nibbles. So 1, 2, 3, 4. 1, 2, 3, 4. Right. And then you write the positional values 1, 2, 4, 8. 1, 2, 4, 8. And then represent them as a denary number. Right. So what is this? 12. This one, 8 plus 1 is 9. Okay, so 9 is fine. 12. Tarul, can you tell me what 12 is in hexadecimal? Tarul, who is this Rainbow? Rainbow, can you tell me what is 12? Yeah, 12 is?
C.
C or D?
C.
C? You mean C?
Yes, sir.
C, no?
Yes, sir.
A is A is 10.
A is 10, B is
B is 11.
11, C
Yeah,
is
yeah, yeah.
C is
9C,
12.
right? That's 9C. Okay, write it down. And lastly, we'll take we'll take 2D. 2D to be converted into binary. So D is, what is D? If C is 12, D is 13, right? D is 13, 2 is there. Right. So what you do is you write the positional values 1, 2, 4, 8. And then for this one, for 2, we write 1, 2, 4, 8. So how do you write 2? There's 1, 2, no ones, no 4s, no 8s. 13, that's 1, 8, no 4s. No, sorry. 1, 8, 1, 4, that's 12, and 1, 1, that's 13. Okay, 8 plus 4 is 12, plus 1 is 13. and you write the answer 0, 0, 1, 0, 1, 1, 0, 1. If they don't want 8-bit number, you can omit the 2 zeros. Otherwise, just keep the 2 zeros. So this is the answer. Is that correct? Is this correct? You also do it, huh? Is this correct? Anyone?
Yes, it's correct.
Correct, no? Right, okay. Okay, finally, I'm going to take another one, a new one. So now the groups did this. This can come in the exam. I'm talking about this one. Perform the following calculation in binary. Perform the following calculation in binary. 25 plus minus 13. 21, 25 plus minus 13. How do you do this? For this one, we need to use 2's complement. Now the 25 is a positive number, so we can use the normal binary conversion, right? For minus 13, we can use 2's complement. To represent minus 13, we can use 2's complement. And then what you have to do is this bit pattern and this one can be added together. And that's why we learned binary addition. Okay, shall you do it? You also do it, right? Okay, we are going to perform 25 plus minus 13. So instead of deducting 13 from 25, what computers do is they represent minus 13 in 2's complement and add it to 25. Okay, so let's do it. Let's take 25. Remember, we had to do it with 8-bit binary. So 25, how do you convert into 8-bit binary? Write the positional values 1, 2, 4, 8, 16, 32, 64, 128. That's 8 bits. Okay, so let's put 25 into this. There's no 128s, no 64s, no 32s. First watch, okay? First watch, then you can write. Do you have 16s? Yeah, 116, 25 minus 16. Balance is 9. There's 1, 8. Balance is 1. Okay, you put that one here. And these will be zeros. Okay, that is 25. Okay, now you know how to convert 13, right? 13 into, minus 13 into 2's complement. Can Ayatma tell me, how do you convert minus 13 into 2's complement?
So first write the positional value.
Okay, yeah, first write the binary pattern for 13, not minus 13, but 13. So if it is 13, you know, it should be 1, 8, 1, 4, that's 12, and 1, 1. Okay, that's 13. The rest will be zeros. Make sure that you fill zeros to make it 8 bits, okay? Before you convert to 2's complement. Right, anyone finding it difficult, let me know immediately. Right. Okay. Now what? What's the second step, Naila? What's the second step? Naila, what's the second step? Yeah?
You convert it into a model one.
Convert
Where you take the last bit. The
A.
last.
We just converted 13 into binary. So what's the next step in 2's complement?
So you flip
Keep
You
the
flip, yeah, that's right. You flip the bits. Okay, so 1 becomes 0, 0 becomes 1, 1 becomes 0, 1 becomes 0, 0 becomes 1, 1, 1, 1. Okay, what's the last step?
You add them.
Huh?
so you add 1.
Add 1, yeah, that's right. Add 1. Add 1 to this flipped bits, right? Flipped bits. Add 1. So 0 plus 1 is 1. This is 1. This is 0, 0, 1, 1, 1, 1. Okay, now we have got minus 13 in 2's complement. Right, what do you have to do now? You need to add this bit pattern and this one. These two should be added. Okay, let's take them separately. Right? Okay, this is 0, 0, 0, 1, 1, 0, 0, 1. Then this means 1, 1, 1, 1, 0, 0, 1, 1. Okay, let's add them together. 1 plus 1 is 2, so you keep 0, take the carry bit to the other side. 1 plus 1 is 2, keep 0, take 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 2, keep 0, take 1, and 1 plus 1 is 2, keep 0, take 1 over there. 1 plus 1 is 2, keep 0, and take 1 there. 1 plus 1 is 2, keep 0, and take 1 there. Okay? Now, what do you notice here? What do you notice here?
So it's an overflow.
There's an overflow. There's an overflow, yeah. 8 bits, 8 bits, and this one is 9 bit. Okay. Now, if you add these two numbers, what is the expected result? If you add these two numbers, what is the expected result?
So 12?
12.
Because
it is 12. Right?
Yeah.
Okay, so in this case, because we are supposed to get a positive number, we can discard this overflow bit. Okay, and then check this out. Right? Check this out. This is 1, 1, 2, 4, 8. 8 plus 4 is 12. There you go. So the answer is this, not this one. Eh? So we have to discard 1 there because we are supposed to get a positive answer. So this 8-bit pattern is the answer. Understand? Clear? Is it clear, everyone?
Yes, sir.
Yes, sir.
Okay, so remember, when a question is given like this, don't forget to convert this minus number to 2's complement. Positive number, we don't need to convert like this. It's only the minus number we convert to 2's complement. Positive is as it is. And then you add the 2's complement value to the positive binary value. And then you get the answer. If the answer is supposed to be a positive number, discard the extra bit, the overflow bit, and write the rest as the answer. Okay? Understood?
Yes, sir.
Okay, guys, then that's it for today. So I'll be having the class the usual times. If there's a need for a change, let me know. Actually, oh yeah, someone asked whether we can have it on Friday. What about others instead of Thursday?
I'm fine with it.
Friday
I'm fine.
30. Anyone who doesn't like that idea can
Sir,
raise.
Friday will be good.
Friday is good, no? Nabil,
Yeah.
I
what
have a
about?
class with Friday.
Huh? You have a
So I have another class at 5 to 9
5 to 9, but
on Friday.
but I'm having at 10:30.
Okay, sir.
Okay, no, right. Then shift is shifted to Friday 10:30. Okay, then see you. Good night.
Okay, sir. Thank you,
Good
sir.
night, sir.
Thank you, sir. Good night,
Welcome.
sir.
Have a good night, sir.
Okay.